Now you turn it in. How about that? Just I want to hear about you guys doing it. Sorry? Too hard? It's not easy. I accept it's not easy, but I don't think it's too hard, But it's not easy.
I think it was too difficult, but some of it was more difficult than like the examples we covered in class. Like a little bit different.
No, I covered the midterm question, right? That was exactly. I don't think any of them were more difficult than that, right? So the one was the most calculation. It was 2 parallel loads. That's it. Instead of 1 load was 2 loads. That's it. That's the only difference you can see with what was in the midterm exam.
Number 3 was so confusing with all the variables.
With what? Which variable?
The part 2, number 3 says you had asking for all the variables. It got kind of confusing because you thought it would be done.
Yeah. Number 2. Which one is the number 2? Is this
part 2 of number 3?
The one it has a capacitor switching or not?
No, number 3. So it's just asking for all the variables.
Yeah, but that one, see if you look at that number 2, just like we told you, I think the load voltage is something, I believe, right? I don't know, 14 volts, something like that, 4160, something like that. The only point is for that problem when you are solving it, that if you have the homework, just use the liquid step, okay? To make sure I'm not talking wrong.
He's talking about the last problem that was supposed to be.
Oh, this one, yeah. So the last problem, the last problem is the easiest one. I would say.
It's so confusing because there's so many variables aren't they the same thing?
That's exactly that was the intention. As I said, I asked Arnold to put this problem number 1, but it was a little bit miscommunication between me and Arnold. Because this is the easiest. Meanwhile, the easiest one is the most, concept, for you to understand the concept of this star and delta connection, That's I want you instead of going through a big circuit, you're worried, okay, how should I solve this one, how should I solve that one? Just I give you a very, very simple example. Just you can play with the line voltage, phase voltage, line current, phase current. That was my intention of this problem. This is very, very easy, there's not that much calculation. But the intention of this problem was to get you guys a little bit more, involved with this problem, and you understand the star and delta connection. Okay? Homework, maybe I'll go Thursday afternoon, very quick. I'll go over the homework. But he's going to post the solution, not tomorrow, maybe the day after tomorrow. Okay. Yeah, he's going to post the solution, in a day or two. First he's going to post the new homework, and after that we'll go for the solution.
For problem 1, when we converted the voltage from line to line, we didn't know what the configuration of the power source was.
Phase to line?
Yeah.
If I don't tell you what the source configuration, which one is easier for you guys to deal with?
Star.
Just go a star. Whatever I think. It is usually a star. We'll go a star. If I don't say anything, we'll go with a star connection. Because it's the easiest one to deal with, just go with that. But if you look at problem 1, so just problem 1, if you look at it, the diagram shown in the figure below has to be 2-3 phase load, and that from a manufacturing plant. That form a manufacturing plant, right? They are connected in parallel and require 4.16 kV. So I'm taking the load side, right? This is the only thing maybe is a little bit you guys can see, but this is the load, right? And you have this. This load is basically this star and delta thing. I put everything. It says here is the 4160, right? So you are going to change everything to a star for this one, right? So because this one is given, when I do this delta star connections and everything, I'm going to change the delta load also to the star load, right? To create the see, this is the 4160 here, right? This is the 4160, right? Here, basically. That's the load voltage, right? How much is it here? How much is it here?
460 divided by square root of 3.
Right?
angle different?
So hold on. This is the magnitude, right? So this is a phase A, for example. There's an A, right? Or you want to, whatever angle do you want to give this one? Select one. You can select only one. But after that, you have to follow that. Do you want to put the minus 10, for example, here? Put minus 10. Do you want to put 120? Put 120, whatever. But from this point, when you select this one, this is your reference. Everything else is going to be respect to this one. You know what I'm saying? So, what the easiest number to select was that number? 0. 0. Right? And go select. And after that, it's asking, I think it asks how much is the load source voltage, right? Here we have this impedance here. Right? And I'm gonna connect my source. It doesn't say anything. I'm gonna connect my source as a starter, right? I'll put the source like this. It didn't say anything. I'll move. Oh, I made a mistake. No, this one is not that. This one is coming. Right? Now, I think he asked how much is the power factor. Some of the things about here, right? You have this impedance. You have this impedance. This is not actually easier to. When I give you this voltage, it's easier to give you this voltage. Why? Because when you have this voltage, easily you can say how much is this current, how much is this current, right? This voltage divided by this one. This voltage divided by this one. And how much is this current? This one plus this one, right? And you have this current. Now, if you want to find out how much is this voltage, you write KVL here, right? You know the current, you know the impedance, you know this voltage, you calculate the voltage here. Let's just I'm throwing. Let's say you calculate IA would be 5 with 15, for example, right? You calculate in this one. And after you write a KVL here, we get this one, for example, I don't know, 5,000 with 65, for example, right? You calculate this one. Now, we will ask you how much is the, for example, power factor. What's the power factor? Look at this one. Cosine of this angle minus this angle, right? 65 minus 15 is 50. Cosine of 50. How much is the, complex power? It's going to be, these are RMS values. Remember the complex power was half of VMIM conjugate, right? So, VI conjugate, and we use the maximum, but these are the RMS value. What we said is a half of VI conjugate, right, for the complex power. But this one was the maximum value, right? These are the maximum values for the phasor. So you can say either way, which way you want to say. You can say VI conjugate, but these values, they are RMS values. You know what I'm saying? These are RMS values. Either you can say half of VI conjugate and use the maximum value for the phasor, or you can say VI conjugate and just use the RMS values for the phasor. You know, either way you solve this problem. That's it. This is the second problem. This is much easier than the exam question. If you look at it, it's much easier than that. Because in the exam question, you have to calculate lots of things. You know. Now, before starting, they start to talk about the. Any more questions on this homework? Before we go to the transformer, today we are going to talk about transformer. Did anybody work on the two winding system? I wrote the equation is a half of, Li1 square plus half of L22 I2 square plus L12 I1 I2. Did anybody work on that one? You asked me is wrong, right? Well, it's not wrong. Just like because the calculation I give is not wrong. But I went double check myself on that calculation. Any of you who are curious to see I'm right or wrong? We talked about it a little bit. No? I'm curious. Huh? No, I'm saying, did you look at it and say, hey, come here to me, hey, that one is not going to work, but you say, or it's going to work?
We thought that I1 was a constant, you were taking the integral with respect to I2.
Yeah.
So then I1 just comes out front and then you just get I2.
No, that one is not correct. We cannot do it that way. I'm going to talk about it a little bit more on the 2A. After we finish the transformer, we're going to calculate again energy and force and those kind of things. But that equation, the final answer is correct, just to tell you it's correct. But the middle one, I said 0 to I1, I'm going to put there. Yeah. Yeah, this one is correct. Yeah, the final is correct, but that's fine. Don't touch it. That's correct, you know. But we'll work on that. It's a little bit tricky to calculate that integral, you know. We'll talk about it after we finish the transformer. We call it energy conversion. But what I want to tell you, we talked about the self-inductance and mutual inductance and those kind of things. You know, because you have one problem in your homework to calculate. For example, for a 2-winding system, we say it's going to be L11, I1 plus L12, I2, and lambda 2 was L21, I1 plus L22, I2. Right? What I did, how did I calculate the mutual inductance? Just I draw the magnetic circuit, I calculated lambda 1 and lambda 2. I said, okay, the coefficient of I1 is L11, and the coefficient I2 is L12. But there is an easier way to look at it. If I want to calculate L11, I want to calculate this one. What should I do? I said L11 is lambda 1 over I1 when I2 is 0, right? Is it correct or not? Put the I2 0 on that equation, right? Is the lambda 1 over I1. So basically, just let me tell you how simple is this. This is a much easier way to solve it. You can go write all the equation and solve. But let's say, for example, we have a circuit like this. I don't know, we're going to put a crazy circuit here. I don't know, one winding here. This is a it's a 2-winding system, for example. Right? I1, N1, I2, N2, N1, right? Basically, that one, what is saying, when I'm calculating this one, I'm saying, hey, forget this one, right? The current is 0. It's like a 1-winding system, right? How much was the inductance for a 1-winding system? Wasn't it N squared over R equivalent? Right? Remember, I calculated this one, right? So basically, if I want to calculate the L111, it's going to be N1 squared divided by R equivalent. How much is the R equivalent? Let's say we have a one gap here, RG2. I have a one gap here, RG1. Right? I have one magnetic, reluctance here. I call it Rm2. And I have one magnetic reluctance here, right? I'll call it Rm1. And I have one magnetic reluctance here, right? It's going to be like this. Rm3. And let me put this one is going to be like this. So let's put this source back here. Let's call this one P2, this one is P1. Right? This is the equivalent magnetic circuit of that circuit, right? That magnet. Now, I'm saying if I want to calculate my L11, forget this one, right? Just short it, right? If I say I2 is equal to 0, N2 I2 is going to be how much? 0. When a voltage source is a 0, what does it mean? It's a short, right? So basically put a wire here, right? How much is the R equivalent now? From here. I need to look at it from here. Remember from the circuit theory, the Thevenin resistance, So exactly, how much? Can somebody tell me how much is the R equivalent here? Let's call it ReQ1. How much is the ReQ1? Somebody tell me. If I look at from here, How much is the equivalent resistance, reluctance of this circuit?
RG1 in parallel, RG2 and RM2 in parallel, plus RM.
Yeah. Basically, this one plus this one, parallel with this one plus this one, right? Plus this one, right? So it's going to be RM3 plus RG1 plus RM1 parallel with this one, right? RM2, RG2. Right? Do practice this thing. Just don't go with my equation for the homework you're going to see. Try to calculate this kind of thing. Now, how much is the L22? Correct? Right? This one is going to make the calculation much easier for you guys instead of writing everything and you go calculate it. You can do it that way. So basically, this time, this source is 0, right? This source is 0. How much is the R equivalent? So how much is going to be L22? REQ2. Right? And because this is this one, right? Number of turns is N2 to the power of 2. How much is the REQ2?
RG2 plus RM2 plus RG1 plus RM1 in parallel with
Exactly.
RM3.
This one plus these two parallel, right? See, that's as easy as it is. Now, usually if the system is linear, which is linear I mean the Li curve, lambda versus R, or BH curve, doesn't matter. When I'm saying linear, when they have something like this, it's not bending, you know what I'm saying? L12 and L21, they are equal. You can use either of this equation. You can use either this one, you can say how much is it? Lambda 1, right, over I2, right, when I1 is equal to 0, right? Or you can say lambda 2 over I1 when I2 is equal to 0, right? Right? Now, just let's think about this one a little bit. About this. I'm not sure. I'm going to go with this one, for example. I'm going to go with this equation. So what should I do here? I want 0, right? So I'm going to short here. So what should I do now? I need to calculate the lambda 1, right? If I want to calculate the lambda 1, I need to calculate phi 1, right? So basically lambda 1 is going to be n phi 1. When this one is not there anymore, right? This one is not there anymore. Be careful. We have only one source here. If you write the KVL, KCL, you calculate the flux here, phi 1, is going to be a function of I2, right? So times by N1 is going to give you lambda 1. Divided by I2, you're going to get the result. You will see it in the homework. You know, just I want to give you a heads up about the homework when you're going to work on it. Now transformer. We start with the ideal transformer. In this class only we talk about the single phase transformers, not three phase. But three phase transformers they have used everywhere. You know, unfortunately we don't have the time to go through the three phase transformers. You know, we stick with the only single phase. You learn the basics of the transformer. We start with the ideal transformer. a transformer, a simple transformer. A simple transformer. There is a magnetic core here. I put the magnetic core here, right? And 2 windings. At least 2 windings. There could be 3 windings, 4 windings, whatever, you know. Well, at least there are 2 windings. Very simple. What transformers they do, they change the level of voltage from one side to the other side. For example, the transformer could be a step-up transformer. What does it mean, transformer, a step-up transformer? If it's a step-up, what does it mean, a step? This is the primary, we call this side primary, and this is secondary. We go with the 1 and 2. 1 is the primary, 2 is the secondary. What does a step-up transformer do?
V2 is
No, I am not talking about the equation. Just I want to know what does it mean, a step-up transformer.
To increase.
A step-up, when they talk about transformer, they talk about the voltage. The voltage is the voltage, unless they say the current. A step-up transformer, for example, 10 volts is coming, is stepping it up to the bigger voltage. Basically, very simple. V2 is more than V1, right? If it's a step down, we have all type of them, a step down. V2 is less than V1, right? You're reducing the voltage. If we have an isolation transformer, isolation means you want to separate 2 systems electrically. Magnetically, still they are connected together, but magnetically, because there is a flux going through here, these 2 windings, they are linked together through this magnetic flux, but there is no electrical point of connection. This is very important. You know, you see in power electronics too, we have a isolated load converter. All of them, they have a transformer. So basically here, usually, V2 is equal to V1. They don't change the level of voltage. But if they want, they can also change the level of voltage. But isolation transformers, usually, they don't change the level of voltage. Whatever is coming, is going to go up. Now, when we say ideal transformer, there is a few things, we are talking about. Remember, toward the end of the class, I talked about this one. I said there is we have a magnetic flux here, right? V, M, and we have some leakage, right? CO2 and here, right? Every winding, you said it has some leakage flux, right? Now, when we say a transformer is ideal, first of all means R1, this winding, they don't have any resistance. So basically R1, when we say R1 equals to I2 equals to 0. Second, when we say is ideal, means there is no leakage flux. CL1 is the ideal. And let me see, there is anything else on there. The third one is what we talked about the last thing in the last class was the core loss, right? We said we have a hysteresis loss and we have a eddy current loss, right? Then we talked about the ideal transformer. Transformer means P core or PC. Simply we write it PC. This one again is 0. There is no power loss inside the core. That's the third one. And the fourth one, I'm not sure should I mention it or not. This core is a linear. No saturation. Saturation means the curve, the BH curve, we are not going to end to the bending part. It's going to be always linear. So these are these are the assumptions. When we say ideal transformer, we're going to say this kind of thing. Now, so if your ideal, let me draw this circuit. It's going to be like this. There is no resistor. This is the I1. This is the I2, N2, E2. Basically, V1 is equal to E1, right? And there is only flux here. Vm, right? We have only flux inside the core. There is nothing through the air, right? Now let's find out the equation. What are the equations for this system? Based on the Faraday law, we know E1 is equal to N1 dTm over dt, right? That's the voltage here we have. It's going to be this one. How much is the E2? How much is the E2? N2 right? Now, if I divide these two by each other, it's going to be, let's put also this one. Also, so E1 over E2 is going to be equal to what? Just divided by each other, right? The dPm over dt is going to cancel, right? So it's going to be N1 over N2. But because it's ideal, E1 is equal to V1 and E2 is equal to V2, right? There is no drop voltage here. There is no drop voltage here, right? So it's going to be V1 over V2 is equal to N1 over N2, right? This is a voltage equation. How you can step up or you can step down the voltage in time. Now, let's put the magnetic circuit here together. It's going to be like this. Ideal materials. Right. So if I write a KVL here, it's going to be minus N1 I1 minus N2 I2 is going to be equal to plus RMCM equal to 0. If the system is ideal, ideal means the core is perfect. Ideal means the core is perfect. How much is the RM? 0. RM is 0. RM is going to be 0 if the system is ideal. Infinite. Let's say we have a material, the magnetic core, the permeability is infinity, right? Like wire. What's the ideal wire? It doesn't have any resistor, right? Do we have an ideal wire? No. Every wire has a resistor. But in mathematics, we can consider ideal wire, which means there is no resistance, right? Ideal core also means there is no reluctance, right? So what is going to happen? Minus N2 I2. Or, I'm going to put it here. N1 over N2 is going to be minus I2 over I1. N1 over N2 is minus I2 over I1. I'll write it out. So far I have this form. V1 over V2 is N1 over N2 and minus I2 over I1 is the N1 over N2. Right? So basically this is the equation for ideal transform. Now, to show the transformer, we're not going to draw this circuit anymore. They use this symbol. This one determines the number of turns in N1, this is the N2, and this is the E2. I'm going to add one more thing here, dot. You put a dot here and a dot here. This dot, basically they show the direction of flux in this winding. Instead of drawing a physical circuit, just we put the symbol over there and we put the dot. The voltage equation is the same thing here we have, but for the current, this part we call it the ampere turn law. Just learning this, the ampere turn law. Look at here. This is very important because for lots of problems, for some auto transformer, those things we're going to talk about it later, it's going to help a lot. Ampere turn law is said the summation of all the NI, ampere turns, in the system is going to be equal to 0. But how we're going to sum those things together? So here I have an N1, I1. If the current is entering to the dot, we consider it positive. If the current is leaving the dot, we are going to consider it negative. So basically, if I'm going to write the ampere turn law here, this one is saying in general, so sigma Ni is equal to 0. Basically equal to HL. But when the material is ideal, H is 0 or R is 0. You know what I'm saying? Basically, for ideal material, the ideal transformer is going to be 0. Ideal transformer. It is an ideal transformer, H is 0 or R is 0, doesn't matter. They are equal, right? Now sigma Ni is equal to 0. How many ampere turn source I have in this system? 2, only 2, right? So for this one, the current is entering to the dot, right? Basically this one is going to be plus N1 I1, right? For this one, the current is leaving the dot, right? It's going to be minus N2I2 equal to 0, right? Basically, N1I1 equal to N2I2. Or N1 over N2 is I2 over I1. This is a little bit different from here, because here I got a negative. Why I got a negative? Because look at the direction of the current, here and here. This is because of the flux direction. These two, they are helping each other. Here they are they are subtracting from each other, they are opposing each other, right? Here, the flux, this one is generating, let's say if you have only this winding, the flux is going to go like this, right? How about this one? The flux is going to go like this, right? Both of them, they are generating flux in the same direction. But if I change this current this way, right? This one is going to generate flux this way, this one is going to generate flux this way, right? They're going to be opposing each other. It's going to be N1 I1 minus N2 I2. Let's put this one back the way it was.